Hello, folks. All right. For a few terms, I had to put up a what's called a phase diagram for water. And I know this is kind of difficult to see. I've got this turned so the big shiny thing isn't on the video, just off the video. But what I've done is I just looked up the phase diagram for water. You can go ahead and Google it. I just found one on Google, brought it up, and there's some terminology on here that we have to go over. And this phase diagram is going to show that terminology. Of course, you have a phase diagram in your book for water, and there's also one for carbon dioxide. You can check that. It is in chapter 11. I can't remember what page exactly it's on, but you do have to know how to read one of these phase charts. I will ask you some multiple choice questions on your next academic adventure on a phase chart. And this phase chart shows, you can see ice, water, and water vapor. And that ice, water, and water vapor, these are the phases that H2O would be in under particular pressures and particular temperatures. So down here we have temperature in Celsius. Here is 0. I'm not sure if you can see that. If I get it any closer, I'm going to lose the whole diagram, but this is where 0 is. This line right here is 0. And so we can see that under, and this pressure right here, ATM is 1 atmosphere, that's 1. 1 atmosphere is average air pressure. So under average air pressure conditions is what you and I experience, okay? That's normal air pressure. So along this line is where we would want to look to see what phase water is going to be. This is normal pressure. Under normal pressure, water will, 0, melt and freeze at that particular point, meaning that if you're adding heat to the system, you have water. If you're subtracting heat from the system at this point, you have ice. So this line denotes the difference between ice and water, the solid and liquid phase. If we keep going along normal, this is normal pressure, eventually we hit 100 degrees, and now we run into, if we keep going to the right, into water vapor. Water will vaporize, and so this is where the boiling point would be. Now this is under normal conditions. Well, water does all kinds of funky things under very low pressures or very high pressures. You can actually put a lot of pressure on water, increase the pressure, and then look what happens. If we go across, let's actually pick this point here. We go across and we finally get to the boiling temperature. We drop down that boiling temperature for here for water. That's 100 normal boiling and 374. We'll get to that in just a second what that means. We would have over 200 degrees Celsius that water would boil. If you crank up the pressure, we can force water to stay down. That's what you're actually literally doing. You're telling water, no, you will not vaporize. You will stay down there in the water phase. And so that liquid phase. And so you can't get water to boil with a lot of pressure because that pressure is like, you will not vaporize. But if you get it going hot enough, in other words, those particles are like moving faster and faster and faster and faster and faster, eventually they can overcome that high pressure holding them back, and eventually you can get that water to boil. But at high pressure, it's going to take a high temperature because that water is being forced to stay together, and you're going to need a lot of molecular motion to overcome that pressure. A couple of points on here I want to point out. One is called the critical point. That's the critical point. I'm not sure if you can read that, but that's a critical point. And what is the critical point? And what is the critical temperature? So if you look on here, critical temperature, okay, on our list, that would be for water. This is for water. Of course, if it was carbon dioxide, it would be different numbers. But for water, the critical temperature is 374 degrees Celsius. What does that mean? That means that at that temperature, and that is really hot, that is like, whoa, Mississippi in the summertime, hot, that is hot, 374 degrees Celsius, 3.74 times normal boiling temperature for water. That is the hottest temperature. At this point, you cannot, beyond this point, at this critical temperature point, you cannot keep water as a liquid anymore. So as we go up in pressure, we can make water get higher and higher and higher in temperature before it will boil. But this temperature, 374, is so hot. How hot is it? It's so hot that no matter how much pressure you apply to that water, it cannot stay as a liquid anymore. Right? Well, we can keep water as a liquid at 300. We can do that. We'll just have to put a lot of pressure on it, but we can do it. But once you hit 374, that's the magic number for water. That's called the critical temperature. No matter how much pressure you put on that water, it will not stay as a liquid. It will vaporize. Okay, that's called the critical temperature. The critical pressure is the most pressure. That's our thing on here. We've got critical pressure. Next one. The critical pressure is the amount of pressure that it takes to keep water as water at the critical temperature. Let me repeat that one more time. The critical pressure is the pressure that it takes to keep water as a liquid at the critical temperature. So at the critical temperature, 374, water to stay water is going to need 218 pascals, okay? ATMs, I said pascals. ATMs, 1 ATM is normal. It'd be 218 times normal pressure to keep water as water at the critical temperature. So critical temperature, hottest water can get without vaporizing. And the critical pressure is the amount of pressure you would need to keep water as water at that temperature. One other thing I want to point out, this is going to be funny, ready? The triple point. Point it out, triple point. Okay, sorry. The triple point is the point which all three phases of water can exist at once. Now you know water can exist in two phases at once. You have an ice water bath. And an ice water bath is ice and water. Two phases. Okay, you have boiling water. What do you have? You have the water and you have the little bubbles coming up. So you've got water, liquid water and gas. Two phases. Three phases can exist under very specific conditions. And a triple point is where all three phases could exist at the same time. That would be a temperature just barely above the freezing point of water, 0.01 degrees Celsius, and at a very, very low pressure, 0.006 as opposed to 1. But it is possible to have water exist at all three phases under those conditions. So I could ask you a question like this from this graph. I could say, all right, under the pressure of half an atmosphere and 20 degrees Celsius, what phase would water be? So you should look at this and go, okay, let's see, half an atmosphere, that's I don't know, probably about here, and then go over to 20, which is going to be about here. Water would be water under those conditions. Or if I said at a temperature or a pressure of 2 and a temperature of 300. Okay, here's pressure 1, that's 218, so 2 is going to be like here, and 300 is going to be like here. We'd have a gas. Okay, so we should be able to read these charts. There are some terminology terms on here, critical pressure. This is called the critical point, by the way. The critical point is where you have the critical temperature and the critical pressure that exists with that critical temperature and our triple point. All right, I think that kind of would wrap it up. If you want to take a look in your book, you can find one of these at the end of the chapter or chapter 11 if you're a book person, and hopefully you are doing some of the work. If you are doing some of the work, I did assign some questions to these charts, and I will give you a couple multiple choice questions on these charts. I'll have you read them. And I think that's it. I think we can wrap this video up, and this one is a little shorter. Ooh, I bet you're glad for that.